Illustration of binary search approach for longest increasing subsequence. In the last lecture, we learned about binary search approach that can be used to solve longest increasing subsequence problem. What did we learn there? We learned that using binary search approach, we can decrease the time complexity of solving this problem from order of n square to order of n log n. This is what we learned in the last lecture. How was this order of n square obtained? This was obtained using dynamic programming, and we decreased it to n log n using binary search approach. In this lecture, we are going to go through the steps that we learned in the last lecture using an example. We'll take an example sequence and then we'll illustrate you how exactly is the longest increasing subsequence found for that sequence. We'll see how are the entries in tails array filled. This is the core of this algorithm. How are you going to fill the entries of your tails array? This is what we are going to illustrate in this particular lecture. By taking an example, I want you to understand how each step is done by a computer when you ask it to execute this algorithm. This is the point. Let us get into this. Let us take an example and understand how each step is done. First of all, what were the steps that we followed in the last lecture? First thing is, in order to find the longest increasing subsequence, that is the length of longest increasing subsequence, you want an initially empty tails array. This is the initial requirement. You have a tails array which is empty. What are you going to do? At the end of the algorithm, whatever be the length of this tails array, that is going to be the length of your longest increasing subsequence. What is the second step? The second step is, for each element s of I that is present in your sequence, let us say your input sequence is called as S and T is your tails array. So S is a set of numbers which is a sequence that is provided to you, which will be in the form of an array. This is your initial input sequence. What do you want to build? You want to build tails array. This array you are going to build during the algorithm. And whatever is going to be the length of this array, that is going to be the length of your longest increasing subsequence. As of now, we are considering this sequence. In the sequence, for each element that is present in the sequence, what are you going to do? You are going to first see whether the element is greater than all elements that are already present in the tails array. That is, for each element, in case, that is, if this particular element is greater than every single element that is present in tails array, that is, all elements in tails array are lesser than this element, then what will you do? Then you will append this element to this tails array. Otherwise, in else case, that is, if there is at least one element here that is lesser than this element or equal to the element, what will you do? In that case, you can replace this element with the other element. That is, one more thing to be noted here, you are not going to replace any random element. Instead, you want to find out the smallest element that is larger than or equal to s of I. In that case, what will you do? You will replace whatever element you have found with s of I. This is what you are going to do. Finally, whenever you have the algorithm completed, whatever be the length of your tails array, that is your final length. Return length of your tails array. This is your final length of longest increasing subsequence. Here the only complex step is binary search. What are you going to do binary search on? You are going to do binary search on the tails array in order to find the smallest element that is greater than or equal to your element you are searching. So S of I, you will take each element. Corresponding to each element, you will be searching for the smallest element that is greater than or equal to it. This is what you are going to search for. Let us take an example and try to understand clearly what exactly is done in this algorithm. How is this working? What we'll do is, we'll take the same example that we used while we were solving this using dynamic programming. Though we solved it using dynamic programming, here we'll take the same example and solve it using binary search approach. So this will give you a clarity on what exactly is the difference between that approach and this approach, because we are taking the same example. Let us say this is our input sequence. I am taking the same input sequence that we previously used. It had 23, then 10, 57. After this we had 40, then we had 32, then 39. Then there were two more numbers. One is 74 and the other one is 50. These were the numbers that we took while we were solving using dynamic programming. What are we going to do now? Using binary search approach, we'll solve for the same step, for the same sequence. We have a tails array to start with. This is our starting point. Initially, our tails array is empty. It does not have any elements. What are we going to do? We'll take the first element that is present in the input sequence. With that element, you will see if there is a point where you can find the smallest element in tails array that is greater than or equal to 23. In this case, tails array is empty, so you are not going to find any element which is greater than or equal to 23. What will you do? If you are not able to find, you have to append this element onto tails array. As of now, tails array is empty, so you will add 23 to your tails array. So your tails array has one entry now. What is the second step? Second step, you will go to the next element in your sequence. You will search whether you can find any element in tails array which is greater than or equal to 10. If there are multiple elements, then you have to take the smallest element that is greater than or equal to 10. In this case, 23 is greater than or equal to 10. What will you do? You will replace 23 with 10. You are going to place 10 here. After this, you will move on to the next element in your sequence, which is 57. What are you going to do? You'll check whether there is any element in tails array that is greater than or equal to 57. There is no such element present. What will you do? You will append 57 to your tails array. So your tails array is having two elements now. Next step, you will go to 40 in your input sequence. Once you go to 40, you will again check whether there is an element greater than or equal to 40 in your tails array. There is an element. If there are multiple elements, you have to choose the smallest element that is greater than or equal to 40. Here there is only one element greater than or equal to 40. You will replace 57 with 40. This is replaced with 40. Next you will move on to 32. What will you check now? Again the same check. Smallest element greater than or equal to 32. It is 40. So you will replace 40 with 32. Next step is you will go to 39. Which is the smallest element greater than or equal to 39 here? There is no element which is smaller than 39. So you will add 39 to this list. Your list is increasing. That means the length of your longest increasing subsequence is also increasing. Next step is you have to move to 74. Is there any element that is greater than or equal to 74 in this list? There are no elements. So you will append 74 to this list. Next element is 50. You will make the same check whether there is any element greater than or equal to 50 in this list. You will see that 74 is greater than 50. What will you do? You will substitute 74 with 50. So you are completed with your sequence. Your algorithm has finished. What can you see now? You can see that your tails array is having a total of 4 elements. This means the length of your longest increasing subsequence is 4. This is what we found out from the algorithm. One thing that I also mentioned in the last lecture, I have to mention this again, that do not think that this itself is your longest increasing subsequence. That is wrong. The only point you can take out from this is whatever is the length of your tails array, that is the length of your longest increasing subsequence. But whatever is your tails array, this itself is not the longest increasing subsequence. Don't think that for this particular array 10, 32, 39 and 50, this is the longest increasing subsequence. In this particular case, it so happened that it actually is, that is 10, 32, 39, 50. It itself is the longest increasing subsequence in this particular case, but it need not always be the case. We had explained about this in the last lecture, that it is possible that this order can be disturbed by some element. Because of that, you can't always say that this will be the case. How will the order be disturbed? Let us say you have one more element here, which is 33. If you have 33 in the sequence after this, if this is the case, what will happen here? You will again check for 33. If there is any element greater than or equal to 33, what will you find here? You will see that 39 is greater than or equal to 33. So you will substitute this 39 with 33. What happens then? 10, 32, 33, 50. There is no such sequence that is present in the original sequence. In the original sequence, there is no subsequence of this order 10, 32, 33, 50. See, 10 is here, 32 is here, 33 comes after 50 in the original sequence, which means it is not a subsequence. For this to be a subsequence, these elements should be occurring in the same order in the original sequence. This is violated here. This is the reason why whatever is the actual tails array that you are building, that itself need not be your longest increasing subsequence. The only point you can take out from this is, whatever be the length of your tails array, that will be the length of your longest increasing subsequence. What is the time complexity here? Coming to time complexity, each time you are picking an element and then doing a binary search in the tails array. So binary search will take order of log n time. For each element you are doing a binary search. So order of n into order of log n will be order of n log n. This will be your time complexity for this algorithm. What about the space complexity? This tails array is the additional space you are using, that is of order of n. So your time complexity is order of n log n, space complexity is order of n.